Okay, we have a situation where we have a relatively thin tube with a certain cross-sectional area ACS. It doesn't have to be a tube, it can be any shape as long as it's got a, doesn't even have to have a uniform cross-sectional area, but if we've got a constant velocity here, then it pretty much does. And we have some area of the area A sub exit slash CS or dash CS, actually it's an underlined CS, of the hole from which water is exiting. Okay, it doesn't have to be water because we've just kept the density at rho, and of course we're neglecting dissipative forces, friction, pressure loss due to friction with the hole and so forth, and with the inside of the cylinder or whatever this is. Okay, what happens is if this cross-sectional area is not a whole lot greater than this one, then you could have a significant velocity at which water is descending here, meaning that if the water that's exiting here is already moving, then all we have to do is change the direction of that motion, which doesn't require any work, and we get some of the velocity that we have for the exiting water. And Bernoulli's equation takes care of that, because you're going to have a 1/2 rho v squared term for the water inside and a 1/2 rho v squared term for the water on the outside. Now, we'll note that the pressure here is equal to the pressure here. Now, as soon as water is out of the hole, as soon as it hits the surface of the hole, actually, its pressure is that of the atmosphere, pressure here is that of the atmosphere. So that the pressure difference from A to B, well, what is the pressure difference from point A to point B? Now, point A and point B are both moving at the same velocity, so there's no velocity change here. There's only an altitude change, delta y, and a pressure change, delta p, from A to B. And I could be a little more explicit. I'm going to put an AB on the delta y as well as on the delta p. I'm not going to write the AB in on all of these, but while I'm talking about it, I'll write in a few of them. But then over here, it's implicit that the delta y is delta y AB, and actually there are only 3 of them, so let's go ahead and label them. There's an AB, there's an AB, and there's an AB. Okay, so anyhow, we have the delta y from point A to point B, whatever that is, and we have the delta pressure, the pressure change is negative P G delta Y A B, and the 1/2 rho V squared, the change in 1/2 rho V squared, then from this point to this point has to be rho G delta Y sub AB, since the change in the 1/2 rho V squared term between here and here is equal to the change in the pressure from inside to outside. Now, we didn't even really need to get the delta P AB to even note that in order to conclude this. Okay, if we just go from point A to point B, we get this. Okay, well, anyhow, we solve this then for the change in V squared. There's no change in 1/2 rho, so that can come out of the change operator. And we get the change in V squared, just dividing both sides by 1/2 rho. We get 2G delta Y AB. So that the change in V squared from here to here is just this. Now, if the area, the cross-sectional area of this cylinder was large compared to the hole, then the delta V, the change in V squared, the original velocity would be practically 0, and the change in V squared is just V squared, the exit velocity squared. And that's a situation we're familiar with. In this case, we should be familiar with this, but maybe a little less so. The change in V squared is VB squared minus VA squared, the squared velocity here minus the squared velocity here, because we'd have some velocity here, some velocity here. The change in the squared velocity from here to here is this. We also know that the velocity at B divided by the velocity at A by the continuity of the fluid is just the ratio of the cross-sectional areas, where the cross-sectional area of the cylinder is in the numerator, cross-sectional area here of the exit hole is in the denominator, and that's just a very simple reason for that, so I'm not going to discuss it. And you can use the continuity equation, but you want to just think of the volume that's vacated here being equal to the volume that appears here in any time interval, and you get this ratio in a very straightforward manner. Okay, so now I think I need to go from here to here. I was trying to go from here to here. Okay, up here. We just put that all together. And our VB squared minus VA squared is then, well, VB squared minus what's in parentheses is just this multiplied by VA squared. Sorry. Yeah. Okay, solve this for VA, and this we get the reciprocal of this. So this is the expression for VA obtained by solving this equation for VA. Sorry, it's been like 2 weeks since we did this, and I'm a little late in getting this up there. But people took the test within a couple of hours after the review session, and fortunately did well. Hopefully the review session helped. Okay, anyhow, that's equal then to the 2G delta Y AB that we get here. And you should take that back to first principles, energy conservation, and so forth. Okay, not sure why the square is there, but it needs to go here. No, I'm sorry. It does need to go here. Okay. Because what I've done is we factored the VB squared out, leaving us a 1 from here and just this ratio squared here. So that VB squared is this, so VB is just going to be this divided by this quantity that we got when we factored this out. And let me pause a second to see where in the world that came from. Thought that would be obvious. Okay, yeah, it's pretty obvious. We just put this over a common denominator and took its reciprocal so that the square of this appears up here, and then the square of this will go into the numerator here, and this will be subtracted from the square of this, and here we have that now in the denominator, because of course we're dividing by this quantity. We get this, and it's very straightforward. The algebra is very clear. So that VA is equal to the cross-section. Well, I'm not going to read it to you. We can maybe I'd better read it to you because I don't see where that came from. Hang on. There's good reason I wasn't able to make sense out of that, because it was just plain wrong. We're getting toward the end of the session, and I think we were kind of hurrying at that point, but that's no excuse. My bad. Okay. Anyhow, we calculate. Solve this, and solving for VB, not VA. There's another little glitch. Okay, and we're just simplifying this expression, and we factor out the 2G delta Y AB, which is your default exit velocity if the velocity of the water in the cylinder is moving at a negligible velocity. And we then factor out this expression. And if we look at this expression, here we have the cross-sectional area of the cylinder squared. Here we have the square of the cross-sectional area of the cylinder, again, minus the cross-sectional areas of the exit hole squared. Now, if this is much, much smaller than this, then so when we square A exit CS, it's going to become much, 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 much smaller than this, so that the denominator is not going to differ appreciably from ACS of the cylinder squared, and the denominator is going to be essentially equal to the numerator. so that this term is going to be 1, and we do get the velocity, the exit velocity, for a large cylinder, for a large cross-sectional area here. Now, there was a question about what the rate of change of VB with respect to VA is, okay? So we'll address this in another video. This one's getting kind of long, and we're not going to say too much about that, but we'll try to get that.